Okay, we're going to be taking the Fourier Bentley series. If you want to watch the first video on that, I have it in my collection there. This is the second video on this, um, moving the idea forward. What we're going to try to do is generate. We have this function we've seen before in the first video that I made. It generates this graph right here, infinite signal, without using, of course, a infinite Fourier series. And what we're going to try to do, we can see that with this and this, we can generate. We can use other functions to generate, for instance, a sine curve, and then a sawtooth curve, and then a sine curve and a sawtooth curve, and so on. So with these two, we can use formulas like this to generate very bizarre waveforms, infinite signals, waveforms. But what we're going to do is the next step after that with a separation of 1. These have a separation of 1. We're going to have to now start generating functions that have separations of 2, and we'll see why in just a second. Let's go to our TI-84 and go to our graphing area and define the y2, y3, y4, y5 in this manner, with these things right here, these functions right here. I assume you can do that. And if we do that, then if we graph y2, we will get this infinite signal here, where you have, signal goes 1, then 0, 0, and then 1 right here. And so it has a separation of 2 right here. This is 1, this is 2, this is 3 right here. And we make it a height of 1 just for a generic height. So the next one we want to do is just shift this right here, so it'll go over to this right here. We'll call this YA, and we'll call this one YB right here. And notice that it's the same graph, just shifted over by 1. And so that'll be Y2 x minus 1 shift right there. So if you graph Y2 x minus 1 on a TI-84 or any calculator or whatever software you have, you'll get this, according to these definitions, of course. And then the last one we'll make is YC, which is just this, shifted over by another 1, so it's Y2 of x minus 2. And we'll get this where there's a separation of 2, 1, 2, then a signal, the separation of 2, signal, and so on. So now we have a function, YA, that has a function here between 0 and 1, a function between 1 and 2, and a function between 2 and 3. So what we can do is take some function that we've defined in video number 1. I define a bunch of functions: a sine function, or a sawtooth function, or a parabola function, had a natural log function, and so on. And we can multiply like this sine wave times this, and of course it's going to give us a sine wave between 0 and 1. It'll give us a sine wave between 3 and 4, and it'll give us a sine wave between 6 and 7. It'll give us a sine wave. Added to that, we might take the sawtooth wave, a function that I have again in my video number 1. I have a sawtooth function, and if you multiply the sawtooth function times YB, you'll get a sawtooth function right here, and it'll be between 1 and 2, of course, and it'll be between 4 and 5, and 7 and 8. So you have sawtooth, sawtooth, and so on. And then finally we'll take this, and maybe we'll multiply a function that I had in video 1, not video 2. It was a parabola. I had a parabola function. So the parabola's infinite signal times this. So of course, we'll give you parabolas in these regions only. So you have parabola right here, okay? So now you have an infinite signal with this equation right here, an infinite signal that has you know, at the first between 0 and 1 it has a sine wave, between 1 and 2 it has a sawtooth wave, and in between 2 and 3 it has a parabola, and then it repeats infinitely many times. So I mean, yes, you could do that with infinite Fourier series, but it's going to be quite a mess to create that. Whereas we're using now these new functions that we've defined to substitute for infinite cosine and sine function Fourier series. We could do this far easier, first of all. Second of all, when it's programmed, the computers can run their programs a lot faster. And one thing that I don't think I mentioned before in the first video is this is much more accurate. You have the Gibbs phenomenon with Fourier series. It causes messes at the edges of the discontinuities here. And also, and if you only take like 20 or 30 terms to define the function, you know, you're not going to get a very accurate wave signal. So this is fast. It's fast, easy. And it's much more accurate. Okay, anyways, I hope you enjoyed this and have fun playing with these new functions I've found.